How are you doing today, Mike?
Okay, mic check is over. Welcome to episode number 23 of Roid Rage. Today we're going to do this a little differently. We're actually going to dive into detail about the power system on each spacecraft. We have Ashton here to represent Odin.
Hello.
And we have Chris here to represent our next generation spacecraft, Vestri. We thought it was important to go through some of the details of how we looked at both of these spacecraft. Now, I want to remind everybody, Odin, we built in an extremely short time frame, right? Odin was built in 8.5 months from when we started to when we shipped it to the Cape to integrate it on top of the rocket. Vestri's build frame is going to be much more along the lines of about 18 months. Plus, on top of that, we get the learnings of what we learned on Odin. But I think it's still really important to go through those. So today we're going to cover kind of three main things: how we do power generation, how we do power distribution, and what we do with the power to store it on the spacecraft. Before we go into all that, though, Ashton, can you give us a little overview of just what were the basic power requirements for Odin?
Yeah, and just before I get into that, the caveat, I would say we actually built Odin in 4 months, not 8.5 months, because we started April 1st of last year, 2024, and we owed the vibration test report to SpaceX on August 1st. We had exactly 4 months to do it, so it's even shorter. We had more time at the end to kind of test and make small adjustments, but all those decisions were made on the architecture really in the first 2 months, and the decisions were made based on what equipment can we get on this incredibly fast timeline, which I've never heard of any spacecraft being built with commercial parts in that amount of time.
Also not recommended, but I get you. So we should re-say that as that. We had 4 months to actually procure all the hardware so we could get into vibration test.
Exactly. Yeah, we did it. So we got into vibration test at the end of July of last year, just literally 2 days before it was due. But yeah, to answer the question about how we designed the vehicle, we persisted, or we kept from an original design, the propulsion system, which was kind of the heart of the spacecraft design. And that was also going to be the most power hungry device on the vehicle. It had 150 watts, give or take, of heater power available to it. Then actually operating the valves and the thruster itself took about another 100 watts when it was running. So that was clearly going to be the major power draw. We also had already spent a lot of engineering effort in building our flight computer, which was pulling about 30 watts of power on average. And so those two components set the baseline for how much power we were going to need. And then in those first few weeks of starting the Odin design trade, we found the radios we were going to use, we found the reaction wheels we were going to use, and all the other components. And so adding all those up, we figured out how much the total power draw of the vehicle was going to be, with some error, of course. And then we built a power system to that requirement. And again, this was all driven by what we could get on the time frame.
Well, I get that. We have a lot of different modes the spacecraft operates in. Give us some numbers. How much solar power did it generate? How did it do it? And how much did it store?
All right. So we had, on the battery energy storage side of things, we had 400 watt hours of energy. On the solar power generation, we had, going into it, what we thought was 200 watts. And, in the end, we found out we were really only getting about 150 watts in ideal cases. And then the power draws of the vehicle in our nominal mode, where we were pointing the antennas at the Earth and communicating with our ground stations, we were expecting to be pulling about 70 to 80 watts. And that turned out to be a little bit underrepresentative as well.
Cool. Chris, we go to
Yes.
Vestri. We got a totally different spacecraft. Obviously, to give you some context, Odin weighed 100 kilograms, right? It's a much smaller volumetric spacecraft that we did. Vestri, we bumped that number up to 200 kilograms. It's a much bigger spacecraft. We also have a little bit different power requirements. Give us the overview of Vestri at a high level. How much power does it generate?
Sure. Beginning of life, we generate about 1,700 watts of power with the solar cells. We have, the propulsion system is it's still the biggest power draw on the system, but it pulls in about 1.2 kilowatts now, right? As opposed to what Odin did.
Well, so Odin was a biprop system made by
Right.
Dawn. right? So that was really about heating up the fuel tank so we could condition it to fire.
Exactly. Yeah, it was a self-pressurizing system. So there wasn't a third gas in there that was pressurizing the fuel. So we had to heat it up to get to the pressure such that the thruster could fire.
And Vestri, we go to EP thrusters.
Yeah, it's a Hall effect thruster system. So we're actually, we're using an inert gas xenon, which is ionized and then accelerated with electric power that we use from, that we generate from the solar panels. So that's a major difference in the spacecraft, I suppose. Is a completely different kind of propulsion system, right? Getting its power from somewhere else.
How do we do the distribution? How much do we store on it?
I believe they're 500 or 500 watt hour batteries, and we have two of them. So there's, more than double the storage. But, in our mission, we're seeing the sun an awful lot. So, it's not like a Leo design where you go in and out of eclipse all the time. So we're not actually going to cycle those very much. And when we're using a propulsion system, we're going to be getting most of that or getting all of that power from the solar cells at that time.
Cool. I want to actually dive into some of the details of this because I think the devil's in the details of how we design spacecraft and how we think about solar panels. Let's start there as a whole. So the interesting thing is both of these spacecraft actually from a configuration perspective use the same solar panels. And what I mean by that is I should say configuration. They both have two wings and each one of those wings contains 3 panels. But they're still very different in what they generate. So Ashton or Odin, walk us through what kind of panels we use, generation. Give us the whole detail on the panels themselves.
Yeah, for Odin, we used clipped corner triple junction cells with, they're called CICs, cover glass interconnected cell, all in one assembly. It's the state-of-the-art, the highest power efficiency of cells that you can buy commercially these days. And so they're really mass-produced for LEO applications where you want to make use of every square inch of panel availability. They're also very brittle and fragile, but that's more or less the technology that we're using there.
What kind of efficiency numbers are we talking about?
I think these ones are right about like 31.5% efficiency. So I think there are some out there that get a little bit higher than that, but these are pretty high as far as solar cells go.
When we talk about brittleness, I mean, I remember when we did the test to see how much, right before we launched, we did a test with UV light, I believe they were using. I don't remember exactly what you guys were doing. I walked by it and we're checking for if any of the glass was broken.
Yeah, there's 2 ways you can check. You can shine a UV light and that'll make any sort of defects shine or glow. But a more interesting one is you can actually run current through the cell itself. So solar cells are basically LEDs in reverse. You give it light, it generates power. But if you run power through it, it will also glow. And as soon as you make them glow, you can see these cracks just shine like darkness.
How many cracks did we actually have right before we launched Odin?
Not as many as we were expecting. We thought, hey, we'd been handling this a lot, moving it around. We had a few that we had some little glue that we could, UV curable glue that we touched up, but there were, I would say, less than 5 little cracks that needed to be touched up.
How do you fix them?
There's I think it's a 1-part compound that we use that we just, it looks like super glue. You just dab it on to any sort of crack, kind of like you'd see a crack on a windshield. It starts as just a little crumble of glass, but it can propagate. And so you want to prevent it from propagating. So you're going to put that little super glue type material there, and then you just cure it with a UV lamp over about 60 seconds.
So we had all these little, how many cells were on? So when we talk about the panels again, we had 2 wings. Each wing had 3 panels. Mm-hmm. How many of these triple junction chopped off corner cells do we have on each panel?
We had, I believe, 29. There were 3 rows of cells on each panel. The outer 2 had 10 cells, and then we needed to, actually no, we had 28 because the middle row we had to remove 2 cells for our hold down release mechanism. So that one only had 8 cells. So it was 28 total.
And how were they connected to the spacecraft?
Each wing had 3 strings of cells on it. So a string of cells is a group of cells that are interconnected in series. And so if you think of the cells as 3 long columns running all the way across the panels, we had the outer 2 columns had 30 cells in them each, and then the middle column had 24 cells. Those were all connected in series going into the solar array input. So we had 3 on the left wing and 3 on the right wing.
So we had 6 total strings of solar cells that
Yes.
we were pumping into our power management system.
Exactly.
Gotcha. What was the bad design choices we made on Odin that we then went and fixed on Vestri?
Yeah. So a pretty terrible decision in hindsight was to actually tie those strings together at the power management system before they got to our power conditioning unit. So just looking at one string for a moment, say we have string 1 coming in off the left wing, it went to both the A side power conditioning unit and the B side power conditioning unit through a current sharing diode, which is not how the conditioning units were ever designed to operate, nor is it how people typically operate the solar cells. You have losses going through that diode, but then also the 2 power conditioning units were competing with each other for the power coming off that string. And we discovered that, and we remedied it by basically undoing that hardware diode in software by just deactivating one side's string. So we tied them together and then turned it off in software because it was not working very well.
What was the whole, why did we decide to tie them together?
The decision there was, if for some reason we lost power conditioning unit A, we want all of the power to be able to go to power conditioning unit B. So we wanted every string to access both sides of the spacecraft.
So this was really our way to have a single fault tolerant spacecraft still.
Right.
Yeah, but the implementation of that led us to be probably much more complex than we needed to be, and at the end of the day, probably hurt us more because of the added testing.
Yeah, the added testing and also the capability of the vehicle was reduced because we had those diode losses, which amounted to a few watts per string, and then we had to artificially clamp how much current the power conditioning units could take as well. So we couldn't even pull the full amount of power off the panels. So we kind of were hit with 2 different efficiency losses there that reduced the total power available to us.
It's a good thing we get to build the next spacecraft, Vestri, and hopefully we don't do that. Chris, give us the overview of how you've thought about solar panels on this.
Sure. We're not doing that. That's to start. So in our case, we still have, like you said, we have six strings on a wing. And we're actually paralleling 2 of those.
We have, Odin had 6 strings total,
We had
3
6
per
total.
wing. We've doubled that on Vestri.
Right. They're also bigger, right?
Yeah.
So our strings are 16S 12P strings, and then we're putting 2 of those in parallel instead of paralleling them, all, and they're only going into one of our power stages, which we have 6 on the spacecraft. So we have 2 strings coming. Well, they actually sit on one panel. So we have the same 2 wings with 3 panels each, but each panel has 2 full strings on them, and each of those panels, well, actually I haven't determined how they're going to plug in, but 2 of the strings off of a wing go into one power stage. And then we convert the power there, and then and then we parallel the power going out. So we can, we have basically a redundant unit, if you will, has 2 strings and a power stage. And so we can lose any of that. And we only lose just the, 1/6 of the power available on the spacecraft.
Are we using the same glass-coated triple junction cells?
No, we are using triple junction cells, but they're coated with I think it's a polymer, right? They're not cover glass. So we won't have the cover glasses. It's for oxygen, mainly for atomic oxygen, that we don't actually have a problem with in deep space, because that's a low Earth orbit thing. When you hit the atmosphere, you take the damage. And that's mainly what the cover glass is for. But we don't have that as much, but we do have protection with the different.
I thought the cover glass was for radiation. Is that not true?
It also supports that.
It's for both.
Okay.
I'll just say it's conversations like this that make me love diagrams, because we're talking about this wing with this many panels, this string going to this side. And it's like, it's very hard to follow, but if you make a picture, very easy.
It's hard to do on a podcast, though.
Yeah.
It definitely is. It's hard to describe this in very clear, concise terms without somebody who looks at this every day, right? But it is, both of these spacecraft, again, have 2 wings with 3 panels on them, but the configuration other than that is very, very different as we go into it. There's something else we designed in Vestri that we actually don't maybe talk about in the same light, which is Odin, we had to cross couple both solar panels so that if we lost a wing, we could still continue the mission. The flight computers could take up to 40 watts of power. And that meant for us that in certain conditions on Odin, just the flight computers and the basic system being online with the reaction wheels could overpower one side of the wings and required both. That is not the case with Vestri.
Right.
What are the configurations of Vestri that we can destroy a wing or lose it and still continue?
Yeah. So basically, the only thing we can't do if we lose an entire wing is fire the propulsion system at full power. Right. So that's the only system in the spacecraft that needs power from both sides to operate at full power. So to get to 1.2, if you divide, very simply the 1.7 kilowatts or 1700 watts of power that we're distributing, half of that is, oh gosh, that's quick math. It's like 850, I think, 850 watts. So that powers, that's enough to power all of our, our flight computer, which is, I think that thing can, in some modes, it burns like 90 watts when it's thinking really hard, like when it's trying to land. But most of the time in cruise mode, it tops out around 60 watts or something like that. But then we have, the power system that's going to take the power that it needs to run, but it's less, the power management card itself takes less power than that to run. But yeah, so the only time we have to cross power, which we do inside the box, is in order to get the full power on the propulsion system.
I mean, it's even, I think, a little bit more designed to a different level is Vestri can actually still stabilize the spacecraft without the panels deploying, period.
Right.
We don't even need one wing to be extended to stabilize the spacecraft.
Right.
So no panels deploy. Let's say we just totally screw up and they're stuck. We can actually fly the spacecraft.
Right.
We just can't fire the propulsion units for any extended time at any power. We can actually save up enough energy in the batteries to still even fire propulsion.
Yeah.
It's just very slow and non-ideal, right? And really extends the mission. One wing being deployed, we can now operate our Hall effect thruster at about half power.
Right.
And both wings being deployed, we could operate the Hall effect thruster at full power and have some margin.
Yep.
The other thing I think is also important to talk about here that I hear you guys both saying in different ways is we actually measure solar panels a little differently. It's not like we've decided on one way to measure them. And what I mean here, Chris, is using number 1700 watts. 1700 watts for Vestri is actually the worst case power we get when we're farthest from the sun. And as we start to have some thermal heating of the panels. When you're closer to the sun, right, Vestri can have up to, I think, 2300 watts of power at 0.95 AU when it's closer.
Yeah, when you talk about how much power you're producing there, it's very dependent upon a lot of things, right? So there's even, at colder temperatures, you get to produce more power. But the problem is as soon as you get into the sun, you're going to heat up, right? So you're going to drop power just by producing power, so to speak. And then, of course, radiation has an effect on that. So at the end of the life, and like you said, when you're far away from the space, I think I did the numbers, and at like 1.1, we get AU. When our furthest, I think we get like 83% of the power, something like that. But that's, again, based on the temperature, which also has a very wide range. In fact, running the numbers at the end of life in hot, we get about a third of the power as we get at room temperature at the beginning of life. So
I think it's so everybody knows AU is astronomical units, the distance from the Earth to the sun. So when we say, and I believe it's 150 million kilometers or miles, I always get the units wrong because units are super not important, right? Which one is it?
I think it's 93 million miles,
93
right?
million.
It's 150 million kilometers.
Yeah.
Okay. God, I'm going to get units right one day. Okay. That we are. So when we talk about being, about 0.1 plus or minus, to give everybody a sense, we're talking about 15 million kilometers, right? That's the difference we're talking about. It's really dependent on what these panels do. What were we on? What was the range we actually had on Odin?
Oh boy. I think at the time we were sizing it for 1 AU. So we were keeping the distance from the sun equivalent to the of Earth's distance from the sun for the sizing of the panels. The goal that we were designing for was 200 watts at 1 AU, and of course we didn't achieve that through various issues like we talked about already. with too much detail.
So Odin was a different flight map, and we didn't have as big. We had a much smaller window of operation for Odin than we did for Vestri. Again, when you build that time frame, you got to keep it smaller. You got to keep it more concise, and we did. We were looking at an asteroid in 2022 OB5 that was coming very close to Earth-Moon system. It was not far away when we would intercept it. So, yeah, fair point. Odin was designed for a different mission, a non-ideal mission, because we didn't have the time to design it for an ideal mission. Vestri, we could expand that envelope. So there is more asteroids we can intercept at any given time.
Yeah, it's good to know that we're doing an ideal mission. But
how much do we lose to radiation per year?
On Odin was expected to be 3 or 4% per year based on that cover glass.
Yeah, what about Vestri?
That's a good question. We've got a few simulations that we've seen. But I don't think we have a great number yet, but it's probably around 5%, or it's probably within 5% of the 2-year mission. We'll probably still only lose about 5% to radiation, but that's,
I mean, I know
it's a working number.
Yeah. For our math and our power budget sheets right now, it's 10% a year, which is an overestimation of what
definitely
Vestri will do. And that's important though, because we don't want to make the same mistake twice, right? We want to make sure, I'd rather overestimate it than underestimate it as we think about these panels. Okay, cool. So I think we've gone through how you generate power in space, which isn't as straightforward. There is other mechanisms to generate power in space, and I think deep space is really where you start to look at them. Why didn't we look at using something like an RTG for Vestri?
Well, they don't like you launching nuclear stuff.
Yeah, but you can, and you can get away. Like we've done it. Curiosity has an RTG, right? There's certain spacecraft like New Horizons that have an RTG. Voyager has an RTG.
Yeah, and those are generally more for when you're in the, Mars, when you get out toward Mars and beyond, when you can't get the amount of solar power, and they're really expensive. So, basically if you have enough sunlight to do solar power, it's definitely the most optimal system to use in this range. You can get too close to the sun too, but we're not going that far in.
Okay, so just for a cost standpoint is more or less why we didn't look at doing anything different.
Lead time too and availability. I mean, I'm not aware of a commercially available radiothermal generator, which is RTG. So
has one ever flown on a commercial mission?
Not that I'm aware of. I know that there's some studies right now for the lunar village to put some nuclear reactors there, but I think that's like a full-blown reactor, not even an RTG. And that again is not going to be commercial. It's government buying that.
I know Scott Nolan just started a uranium company. Could we just buy some uranium and make one?
We can give it a shot.
I actually don't even know if that's what they run off of. So fair enough. Okay. So we have these solar panels. We got these solar panels that are generating power that go out. I think this is a complexity that we don't actually dive into a lot and nobody really does is you have solar panels. What do you do with that power? So one thing that's not always intuitive to people is you are collecting the power from the sun, whether you like it or not. So if we have a solar panel pointed at the sun, you're collecting whatever that flux is times your efficiency of your cell. That's how much energy you have to do something with. And you can turn that into heat. To be fair, all the waste energy on a solar cell is turned into heat. It goes out the back of the panel. That's a lot of waste energy, right? If we're generating 400 watts per cell, we're actually generating about 1,200 watts of waste heat out the back of the cell.
Yeah. Anything that's coming in that's not reflecting is getting radiated out somewhere.
Somewhere. But we have this big amount of energy that's coming in, and you can't just turn it off. How do we manage that?
So I can't turn off. There's two ways to do it, and the conventional way a spacecraft does that is they basically short out the solar panel. So it's called a shunt, and if you're not using that particular string, you shunt it to the wing itself, and you basically run the short circuit current through the wing, which brings it down to 0 voltage and 0 power. But you're basically leaving the solar power is, the radiation power, radiative power, whatever you want to call it, is coming in and it's staying as heat because you're not pulling it off of the wing.
So you're just dumping that energy into the wing.
It's just getting dumped into the wing. Yeah. So in our system, with the number of strings that we have, I can turn, I said we got 2 strings going into a power stage. Well, I can even turn one of those off, and I'm just not pulling the power off of it, right? So it's just going to stay there. It's the opposite of the short circuit condition, where you have the open circuit condition. So we have the granularity that we get from having 12 strings total that we can use. We just leave them off, and it's not turning them off because the power is still coming in, but it's leaving it out there on the wing in the same way as when you shunt it. It's just staying out there on the wing, and then we have a smaller problem to deal with then, because we have, like I said, more granular chunks of power that we can bring in, and then instead of tracking at the peak power point, because that's what we didn't talk about that, but generally solar cells are operated. They have a IV curve such that as you increase the current draw from them, the voltage decreases. And as the voltage and the current, do their thing going up and down, you get a power curve out of that. And at the knee, basically where the voltage starts to drop off down toward the short or the open circuit the short circuit voltage and the short circuit current, you get a maximum peak power point. And that's what the peak power tracking is, the maximum power point tracking, the MPPT that you hear so much about. And basically that's just operating the solar cell in its most power positive position on that curve. But you don't have to actually operate it there. You can operate it a little bit off of that. And you can leave, it does the same thing. Instead of leaving all of the power out on the wing like you do when you don't turn the power on at all and you have the open circuit, or shunting it to where you have the short circuit, you're operating somewhere in the middle and you're leaving some of the power out on the wing.
So you're just turning on and off all these 12 different strings we have at some frequency?
No, we'll turn them on as we do to cover the mode that we're in. We have several different modes of the spacecraft. We talked about when we're firing the propulsion system, and that's the biggest power one. And, basically that'll have the most cells on, the most strings on at once. But we have other modes where we're, burning like 400 watts of power when we're trying to talk to the Earth really high, doing as much communication as we can. And that burns quite a bit of power because the radio power is quite high, but it's not nearly as high as the propulsion system. But so in one mode, I may have 4 strings on, whereas in, the propulsion mode, I may have, I may need all 12 of the strings on the spacecraft on. And then for the lower power modes, like, sun safe and whatnot, we may have only 1 string or 1 or 2 strings on. And then, the other lever we get to pull is that some of the power can be going into or out of the battery. So the battery can really be used to smooth out the power draw of a particular mode that we're in. So, we set the strings and we're running with 3 strings, for example, and then we need a little bit more power. It can be drawn from the battery, or if we stop using so much power, the extra power can go into the battery and charge the battery.
This sounds complicated as hell. How do we not screw it up?
Well, we have to have a really good control system, and that's where we have our microprocessor or microcontroller that we're using to generate our command signals, basically for our power supplies, is monitoring all of the, basically the current going in and out of the battery and how much, what the voltage is and this and that.
But what if we get it wrong during a mission, Chris? So on Vestri, let's say we get something wrong here. Do we lose the spacecraft? Would we burn up? Like, what would happen?
No, what would happen, like if we're generating too much power and we're too slow to cover it, the voltage on the spacecraft bus is going to rise and it's going to hit a certain level and the protections kick in and you start tripping over voltage protection. For example, if we're not using enough power and we start building.
So we have an extra level of safety considerations there.
Yes, there are more than just that one. There's a lot, because there's a lot of things that can go wrong on the spacecraft. Like the one that worries me the most is if we're running around and we're doing, we're propulsing with our maximum power, and then for some reason a fault happens in the power processing unit of the thruster. And it trips off and suddenly it's not drawing 1.2 kilowatts and I'm still doing it. That's the biggest, change that we're not foreseeing happening. And in that case, it's probably going to be, there's going to be some amount of, you can put some voltage suppression devices on the spacecraft or in the electronics so that when it raises up too much, you can actually, it does the same kind of thing. It'll turn on the device and it will actually short and shunt the extra power to ground. And that's, there are devices that do that, electronic devices. I think the old word was transorbs. They're transient suppression diodes, TVSs, or transient suppression. Yeah, they basically turn on when you get too much voltage and protect the spacecraft. But also, like that would be tripping off the over voltage protections on the power supplies, and they would be shutting down.
So
And
we don't expect any smoke on Vestri.
we don't expect smoke. That's there's no smoke
Ashton,
in space.
On Odin, we had smoke coming out of it. So how did we like? I get you, Chris. There's a lot of complications here on the power side on something like a Vestri, and not only do we have different modes to configure different power draws, we have a whole bunch of secondary and tertiary checks to make sure we don't completely shit the bed.
Yeah,
and we can recover. And that's been a big push on Vestri. Is just how do we definitely level up that reliability to a very high extent. How did we get it wrong on Odin?
Well, Odin was, again, using off-the-shelf parts. So the system that Chris just described is one that we are designing ourselves. For Odin, we were buying the power system from a vendor that was sized for smaller systems than ours. It was capable at our power levels, but it was mostly used at lower powers, like 100 watts and less. And this protection that Chris is talking about when the voltage rises too high because of some transient effects, the way that it was dealt with in that system is through another shunt. They called it the overvoltage shunt. And it had one built into the power conditioning unit itself, but the size of that shunt was too small for the size of the power available to us on Odin. So we removed it and we added an external shunt that could handle more power. And in the assembly of this, we actually didn't assemble it very well because we were in a rush, and the solder joint to go from the shunt to the actual power conditioning unit broke during handling. It was built correctly, but then we basically, it was exposed to the outside, and we set the unit down on a desk one time, and that broke the solder joint. Then the next time we took the spacecraft out into the sun, as soon as a cloud rolled over, or maybe it was the other way around, it was in the shade, and then all of a sudden the sun came out and a bunch of power was available. The voltage on the bus rose. There was no shunt to shunt it, and smoke started coming out.
Got some of that magic smoke. Yep.
Mm-hmm. Yep. So, we investigated it. We found out, hey, this is why it happened. It was pretty obvious once you took a look at it, and we made a more robust solder joint, but still in the end, it was a hacky solution too.
Yeah, the shunts on Odin were really big, and they had to be really big because we had quite a bit of power coming in, and we had to do something with it. And so the fix on Vestri has been a little bit tertiary, but first off, turn off that much power coming so we don't have to deal with it. Let it go out of the back of the panels.
right.
And then second, when it comes to those shunts, keep them very small and very common, and a lot of them.
Yeah, and we basically have to be looking at stuff very quickly. So, it's going to, in the end, the analysis is going to be how fast does the propulsion system turning off suddenly give you a voltage rise? How fast can we react to that voltage rise at our control system based on the things, where we read the voltage going high and we read the current going high?
What are those speeds? How fast, we talk about this MPPT or this tracking that we're trying to do. What frequency is that running at?
We're running at 100 kilohertz. Well, we're doing switching. There's a lot of speed with power supplies is a loaded term. We're switching at 100 kilowatts, 100 kilohertz.
Okay.
And we are controlling the loop at about 10 kilohertz. So it reacts on the order of 10 kilohertz to stuff changing, right? And that's just the control loop. We have protections that can work faster than that, right? Because what happens is, and that's why you have protections, right? Because you're not able to react fast enough. So in the realm of, I don't know, I'm very bad at inverting frequencies to milliseconds or microseconds in my head, but I think we're in the microsecond range in the switching frequency. So we're probably in the millisecond range of, almost the millisecond range of being able to actually react to something. So in that time in between, then the calculations that we do, like I said, is how much does the voltage rise and where does it go and how do we protect it? And it, when you're talking about these like voltage suppression things, which is kind of like a shunt, the principle is the same. We're just shunting the power, the excess power. It's done automatically with, a device. It's, but that device will burn out itself. It can only handle all this current for a short period of time. And so you've got to make sure that the different level of protections you have will kick in before your earlier protections are, well, they let the magic smoke out, right?
Gotcha. And what was the frequency we were running MPPT at on Odin?
I think that was in the 100 kilohertz range as well. I don't know offhand. I could probably find
Disappointing, you guys. You don't memorize all these numbers
Sorry.
for perpetuity. It's very, very, very disappointing.
I can still tell you 8675309. That's been burned.
Well,
into
that's
my
Jenny's
head,
phone
yeah.
number, right?
It is. Right?
Okay. On to some modern topics. Let's go to the last part of a power system, which is the batteries.
Yeah.
Batteries are a fun one. And the reason I say that is in no way, again, I want to remind everybody, we built Odin. We procured the parts for Odin in a couple months. We built the whole fucking thing up in 4 months. Like, it's a miracle we made it this far. I think that was an exercise in going extremely fast. In fact, the vendors we worked with on Odin were all exceptional across the board. The faulting of Odin is all with ourselves and the amount of time we had, right? I think we took a really good shot at it. The fact the thing turned on and got us communications is a little bit of a miracle in and of itself. But like sometimes you need miracles. We did find out some interesting stuff though on the batteries on Odin that I think was just us not really understanding. You want to go into the battery configuration and kind of the limitations we had on the battery that we found out after installing?
Yeah. So, well, there's a few things about the battery, but I think what you're referring to is the total energy available to us. So they are rated at 100 watt hour batteries. We had 4 of these packs. So total we had going into it 400 watt hours. We were using a 4S 2P topology, which means 4 cells in series, 2 in parallel, and that means that the peak voltage of those packs is at 16.4 volts. Our power system could only charge it up to 16.3 ish, a little bit less, meaning that we couldn't really top off the batteries all the way to the top. And so that instead of going all the way up to 100% state of charge, we had to stop at about 90. And on the other end of the state of charge spectrum, when you're under a reasonable amount of current load off the batteries, it causes the voltage to droop. And so as you got into the kind of 20 to 25% state of charge, the batteries would start to brown out. And so that means that we didn't have the top 10%, and we also didn't have the bottom 20% of the state of charge, which really only left us 70 of those 100 watt hours, which is a pretty significant cut to the energy that we had available to us.
Yeah. So what do we do different on Vestri?
Bigger batteries?
Bigger batteries was part of it. I think we also just probably knew what to look for this time and how we designed the power system, but also the questions we asked the vendors and just having more time allowed us to do it. So what did we pick for Vestri?
It's they're like I said before, they're 500 watt hour batteries. They're 8S, which is basically standard for a 28 volt spacecraft bus. It gets you topping out at like 33.6 when they're fully charged. But yeah, you have to take into account, how deep, the depth of discharge they talk about. Ours can be a little bit more because, generally like a spacecraft has a very small or, much smaller one, like a LEO spacecraft, because they cycle so many times. We don't cycle very much, so we can get away with a bigger depth of discharge to actually use more of the charge. But I described earlier how, the battery's kind of a place to sink some current for us when we're trying to balance out our load. That means we want to keep it, we don't want to go above like 90% anyway. So kind of the same thing. That also helps, I charge my car up to 90% or 80% because it helps the battery life, right? It's
what kind of car do you have?
I have a Tesla.
Okay, fair enough. I got no comeback to that. Like Teslas are great.
It's a great
Is it a
car.
Model Y or
No,
Model, what is it?
It's a Model 3. It's the cheap person's Tesla.
I've got the Model Y.
I had the Model 3, but I sold it.
Yeah. It's nice. I love it, but and it drives for me.
But it is. It's why you don't fill your electric car up all the way because you do see battery degradation when you top them off.
Yeah,
right?
I do that. I worked for a battery company. Ever since I worked for a battery company, no electronics that I own go to 100% ever. I got my phone set, and anybody listening, you ought to do that too because it definitely adds the life to your battery and your laptop and everything.
When we go to flight, when we go put this thing on Falcon, are we going to charge to 100% or are we going to stop at some arbitrary limit?
I'm actually not sure what the rules are. We'll probably charge it up pretty high then, though, because we'll probably if they let us, I'm pretty sure
they let you go as high as you want.
Then we would go to 100% in that case, because just like if you're going on a a trip to the airport, you charge your phone all the way up. You want that extra charge. So when you want it, you can have it.
But what you're saying is through all our hard run loop testing and spacecraft checkouts, we'll only go to 80 or so ish percent to preserve it.
Right. And then even when we're cruising, when we're on, out, not the reason we charge it up all the way on the launch pad is so that we can make sure that we have the most amount of time that we can sit on the spacecraft and the most amount of time that we can operate without getting the solar panels deployed and all that.
What is the amount of time on both these spacecraft that we could sit there on the launch pad with the spacecraft off before the battery dies?
I think they're both pretty long. If the batteries are inhibited in both Odin and Vestri's case, the quiescent power draw, which is like the parasitic draw of the battery control circuitry, is pretty low. We're talking months on the pad before we would need to charge up and top off.
Yeah, I think for Odin it was about 500 days, and for Vestri the calculation leads you to like almost 2.5 years.
Right.
So it's a pretty long time.
Yeah.
The other thing that's important for everybody to know about batteries is we talk a lot about batteries and voltages and cells. That's actually probably the least important part of the battery. These batteries also have integrated battery management systems. We do not build that, and there's some complicated circuitry that controls both how you charge and discharge the batteries. On lithium-ion batteries.
They're more complicated if you haven't designed the packs before. I have, so it less intimidating to me. But basically what the BMS does is it monitors the voltages on all the cells. So that when you get towards the top of the charge, it'll bleed off some of the extra charge because you get an unbalanced charge because they're sitting in series and you're just pushing current all the way through like the 8 cells in a series string. And that they don't all charge. They age differently. I mean, when they build these packs, they actually match the cells. So they'll like get them and they'll actually bin them in different groups and they will group those together that act the same, so that you get, it helps with keeping them balanced. But over the lifetime of the battery, they get to where one cell's more healthy than the other. And any battery is only as good as its weakest cell. So like the capacity of your battery that you're seeing is based on the weakest cell, because when you get to charge, at the top of the charge, they start bleeding off the charge from from the cells that have higher voltages, so they can balance them out, right? And then, of course, the other thing that the BMS does is it monitors the currents going in and out and monitors the temperature. And so you can't charge a battery below a certain temperature because it's very damaging on the battery and very damaging on the battery.
What is that temperature range for us?
I think it's like, you will probably want to be around 20 C, but I don't actually know what I can't remember what.
Do you know what it was on
the
Odin?
limit is on this battery?
The discharge temperature limit?
Just what temperature limits were?
0.
0 C?
Yeah, and a big difference. The Odin batteries had per cell heaters, and the BMS was doing its own temperature control, so it would kick on the heaters if it got down to about 5 degrees.
It had little heaters on every cell?
Yeah, little flex heaters wrapped around each
That's kind of
cell.
cool.
Yeah, so this one, they don't have any sort of temperature control. They've got temperature monitoring and telemetry coming out of it, but it's on us to manage the heat.
Yeah, so you greatly extend the life of the battery if you warm it up before you charge it. That's like if you ever do anybody who charges a car is familiar with, well, if you do it in a cold area, probably not here in Southern California. But it has
we don't
to
have that
heat
problem
up.
here.
Yeah, in Tahoe, I have to heat up my car. It heats up and it'll charge really slow until it heats up. But that's the same thing. It won't charge below a certain set, and we will have, you have the heater on to try to get it up to that optimum range. And on the other end, it'll cut the discharge off if it gets too hot, right? Because you'll be discharging anything you discharge through the battery is basically running through the series resistance of the battery. And causing heat to go. And at some point it becomes dangerous. And you get something called thermal runaway. And that's when the magic smoke comes out and you get a very energetic reaction that nobody wants to see.
That's why we have special fire extinguishers here, right? Because you can't just put them out in the same way.
Yeah. Lithium fires are not fun.
Okay. Anything else we need to cover on the power system from either side? Do we miss any key pieces about how these spacecrafts kind of turn on?
Well, there was one thing on Odin, which is another architectural decision that we made, in that we did not pool the power from the two sides of batteries together. So, if the A side was operating, it was kind of two different power systems operating in the same spacecraft, and they didn't share power or really communicate with each other all that much. So the A side had its 2 batteries and one, well, I guess they were sharing the solar strings, but not very well. So it had its batteries, the B side had its batteries, and all of the A side devices were powered only by the A side batteries, and likewise with the B. And that effectively meant that all these numbers that we've been talking about, the 200 watts of solar array, the 400 watt hours of energy, were cut in half effectively at an operational level on the spacecraft. And so we're taking it a little bit different approach on Vestri.
Yeah, that's the circuit I jokingly call the magic circuit that I'm working on now. So I have to make it not magical, right? But basically, to parallel batteries, you need to make sure they have the same voltage or very close to the same voltage. Because if you just if you put, that's why you don't use an old battery. They always tell you don't use the old batteries. Don't mix batteries because they have different voltages. And like if you put two parallel batteries in parallel, they're not at the same voltage. You get a big current. And you can cause some of those things that we talked about a minute ago with the thermal runaway and bad things happening. So basically you have to condition the batteries to be about the same temperature. About the same voltage, state of charge. That's the other thing that BMS does that we didn't talk about was see what your state of charge is.
Count the coulombs, right? Count the electrons.
Which we're going to have to build into our system because the BMS in the battery doesn't do it. It just relies on the voltage, which is not a very reliable way.
Yeah, the voltage curves on lithium-ion batteries are really flat. So it's really hard to determine if you're at a higher charge or not until you get above 15% to the top.
Yeah, it's pretty close.
All of a sudden it shoots up and then
a lot of the BMSs don't even snap to until you hit about 95% of charge, the voltage, and on that flat part of the curve, the temperature actually has more to do with what the voltage is going to read than the state of charge. So, and then so you get them to the same place on the state of charge, and then you carefully connect them together in parallel. You can even do some pre-charging through a resistor to make sure you don't get that big surge of current, depending on how much power or energy we're talking about, it can be, you got to be careful.
But it's really hard to have a two-string system that works with each other, right? It's not non-trivial. And I think what you're actually discovering here is it's not as easy as just putting more batteries on there and pretending they all work together at the same time. Like making these things work and talk and connect and share power between each other, and having the ability for one side to go down and the other side to pick up the slack is really, really non-trivial. It requires us to make a lot of detailed architectural decisions. And on Odin, we had the added caveat that we had 2 months to procure parts and 2 months to assemble it. And that adds another layer of we can't make all the ideal decisions we want because those parts aren't available. So we get another stab at it with Vestri. I think we learned a lot with Odin, and I think the power system on Vestri is already going to be leaps and bounds better, primarily because we have more time, but also because I think we learned a lot from our mistakes of what we did wrong and what we really need to account for.
Yeah.
So awesome. Okay, let's go into some mailbag questions. So some of these are from external people. Most of these are from people in the company that are just trying to talk shit. So I'm going to remove them. Okay, first we have from Loy. In what form will the material be delivered back to Earth? I don't expect an ignet of platinum to be stuck in a reentry capsule, but maybe some enriched process ore. Ashton, you want to take a stab at this?
Sure. We are going to be refining the ore on the surface of the asteroid, extracting the platinum group metals from the iron, and sorting it into our reentry capsule. I imagine that the material will be quite porous and be basically nanoparticles and microparticles all clumped together. So it's not going to be a solid, like you say, ingot of metal. It's going to be a bunch of clumps. I'm not sure what it's going to look like.
That's pretty good for not as paying attention to the refinery at all. I like that. Yeah. Now, the way this works is we essentially create a kind of sand, and that sand is very, very highly enriched platinum group metals, about 95% platinum group metals, removing everything out. That's what we create as of today. So that's what it's going to look like. But all those platinum group metals are going to be together. It's actually very difficult to separate them out without using chemicals. And so what we then do is bring what is referred to as a doré bar to final processing. And that's what most of our contracts are with. So we won't do the final processing of taking this highly enriched sand to a platinum bar. We'll let the people that are experts at that do it. There's not a lot of value that's accrued at that stage. So we're not going to attempt to do it. Okay, from Rohan. As the company that is setting an aggressive schedule, how do you prevent schedule chicken? Chris, what is schedule chicken?
It's basically where everybody competes to not be the long pole on the chain And nobody likes to admit when they have like a slip, right? So you got a bunch of people, their stuff's due, and they pretend that it's due until somebody else says, well, I'm late. And then they don't have to be the one that says, well, I'm late. You know,
How do you fix it?
How do I fix it? I don't know. I try not to be the long pole on the tent.
We kicked Robin off this episode, and Robin would be the great one to answer this, right? But I think that the real way you fix this at a company is schedule chicken applies that you have tight coupling between each deliverable, i.e., Chris, you need to deliver your avionics to software. Software needs to write the code and deliver it to the test team. The test team needs to then test it. And then it's really easy for the test team to say, like, Chris was a week late. We have nothing to do for a week. So what do you want me to do? Like, that's on him. The number one way you deal with schedule chicken is decoupling schedules and saying to the software team, find a way to show me that the code is working without having the hardware. Understanding we're going to have to do another test. Hey, test team, make sure everything is good to go and make your deliverables not tied to there being actual hardware. You can still have a test plan. You can have the simulator up and running. You can have all these other things ready to go. And so the number one way I think we handle it here is decoupling as much as possible the schedule. As soon as it becomes coupled, it's really easy to blame other people.
Yeah, it's like the hardware in the loop tester. We integrate actual hardware as we go, but we start off with like demo hardware, you know, where we have the actual processors that we're using. They're, you know, just not on our boards, you know, so.
Yeah. Rohan also had a second question, but to be honest with you, it's like probably 5 sentences, so I'm not going to read it. Let's skip on to Levi. Hello, asteroid enraged. The structures talk from last week got me thinking, is there any part of the flight envelope other than launch that really matters from a structural or vibe perspective? Ashton?
Absolutely. We are going to be landing on the surface of the asteroid. That is an impact. It's a shock event.
Yeah, but let's be real. Let's be honest here. The answer is no. Like, the shock event landing on the asteroid is less than 1 meter a second of impact force at, what would be a 200 kilogram spacecraft. We have to survive much, much more of that on liftoff at a very high vibe standpoint through the whole first stage burn. It's really the first stage burn that drives these loads, and that's orders of magnitude more difficult and harder to deal with. Once we get past that, it doesn't matter.
Yeah.
In fact, we've had discussions about, rockets do staging. Is there parts of the spacecraft we can have on that are structurally significant to get us through launch and then remove after that allow us to have more delta V? Because delta V is essentially a calculation between the mass of the spacecraft versus the amount of thrust you produce, right? I should say the amount of ISP you produce. Regardless of all that, that's a really dumb idea and didn't really make any sense to us. But no, there's not. Launch is the main thing.
The only thing I'd add to that is if we were doing a different mission, that could be a different answer, right? So if you're doing an Earth observation or trying to take a picture, you have to be really steady. They don't like to move around, and the wings can have modes in them that will shake cameras, but we don't have that issue.
I think large spacecraft have modes in the wings. I mean, ISS famously has modes across its gigantic solar panels. You have spacecraft trying to go to VLEO. That's a very different thing. People landing on the moon, that's a very different thing. I'm not going to pretend this is a lunar lander, right? Lunar lander, a lot more gravity, a lot more force. For us, though, the one thing we have to care about is from the structure is the launch, and that's about it for Vestri. Now, for the next mission, which we'll do reentry, I still think it's going to be launch, but there is a lot more math and more simulation to do to confirm that.
And a lot of thermal in that one.
Oh, yeah.
A lot of thermal. So where are we placing the accelerometers on Vestri? And what's your secret for keeping Vestri's first mode high? I don't know. Every time we go to these, the techs place the accelerometers and help us understand where to model them.
The accelerometers, so this is not the flight accelerometers. This is the test.
That's not defined in this question.
Okay. I was thinking of the flight
but
one.
when he says keep your first mode high, I'm assuming he's saying test accelerometers.
Yeah. So, we submit a plan to the launch provider. They approve where we say we're going to place them, where we put them on critical joints, so at the hold down mechanism for the solar arrays, at some critical points on the base plate. And how do we keep it stiff? We do a lot of analysis. We're going to go to a structures vibe in about a month here, and we're going to see does the analysis match up with reality. It's going to have a bunch of mass simulators in there. Just a lot of design and iteration.
Yeah, it's really as high as we can stand, though, right? Because we want to get rid of material, right? So it's not just
when it comes to mode, if your mode is too high, it means you're too stiff. And so you want to it means you're over mass.
Yeah.
And if your mode is too low, SpaceX won't let you fly.
Yeah.
So the trick is to be over 40 hertz,
right?
but not much more over 40
Yeah.
hertz. And how much margin do you want to hold is a question that we always got to ask ourselves,
Yeah,
right?
exactly. That's what I mean. You want to hit your mode exactly or as close as you can because anything else is too much, right?
Yep.
Too much weight.
Okay, from Lawrence. Does AstroForge plan on eventually hiring an in-house planetary scientist, astronomer, or will you always contract out to folks like Dr. Thomas and others? Asking for a friend. TBD. I think when it comes to hiring planetary scientists, we probably at this point don't need a full-time planetary scientist, especially with the staff we have or the consultants or contractors we have that are doing amazing work for us. It's actually working out really well. And in the planetary science community, access to telescopes, access to the network, being able to check with each other. It'd be really hard for one person to have all those skill sets of how to do this all. And we're finding out is this is actually a lot of little skill sets that need to be put together. So trying to hire one person to do it all, I'm not saying that person doesn't exist. I'm saying we haven't found that one person yet. And it's working out so well on a contract basis for these scientists that can still stay at university at the same time. That's working out great. And some of the best help we've got on this team is from some of those contract scientists. From Ken, on the Vibe Check episode. Oh, so we at least had one listener. That's good to know. Wesley mentioned a final functional test at the Cape before integration. If something does go wrong pre-integration, what are you unable to resolve in time? What does this look like on a rideshare? From an AstroForge perspective, is it a use it or lose it on the launch? And from a SpaceX perspective, do you know if they have a backup rideshare tenants? Or do they use mass simulators?
Yeah, if you are not on the rocket for the rideshare, they are going to use a mass simulator. We don't get to dictate that, and they have carefully balanced the vehicle based on us being there. So if we're not going to be there, there will be a chunk of metal in our place.
And we will spend a lot of money to fly a paperweight.
Yep, exactly. In terms of what happens if something goes wrong at the Cape, there are some stipulations for rework that is allowed by SpaceX. You can unbolt and do a few things, but it's pretty limited. So it for the most part, figure out how to fly without it. You also are super pressed for time. It's not like you have weeks and weeks there to troubleshoot, open things up, ship a replacement. So you go with a fully equipped tool belt with all the possible spares you think you could imagine in any number of situations, and you try to plan for as many of them as possible. But the reality is if something major breaks while you're in the integration facility, there's not much you can do.
Yeah, I think it comes down to the thing, and we were pretty open about this on Odin. We did a functional checkout. We had stuff that we realized was incorrect. And we could have replaced it with a piece of metal and say we didn't make the flight. People have done that and been able to say like, oh, we missed the flight because of X, Y, or Z. Or we could strap that thing to the side of the rocket and pray. We chose option B, right? And like, again, we made contact with it. We made, I think, what is the farthest commercial contact with any privately funded spacecraft ever. That's not a small feat to do, especially for something that was built as fast and as hastily and in the state that Odin was. So, yeah, you might figure out something's wrong. We did that. You might also decide to say, fuck it, let's go for it. Okay, from Jordy. Last Thursday, you mentioned crimson solder in passing, and it made me wonder, what kind of electrical connectors do you space folks use? Are there any superior vibration-tolerant crimp fittings, or is this the same stuff the rest of us use? Well, Jordy, I don't know what you do, but the rest of us usually don't use crimp connectors. But I'm assuming you're talking something along the lines of automotive crimp connectors, because those are probably the most common case. And I think the answer is we absolutely do not use those. Ashton, you want to go to some details of what we use?
We use crimps and solders, solder cups on connectors. To be honest, I couldn't tell you what type of crimps we use. We use the one specified for the connectors that we're using. And we're using aerospace grade D subs for the most part. So I'd have to defer to our technician teams who do amazing work on our harnessing. I couldn't tell you what they were.
I mean, a lot of this stuff is specified for when we need to do it. If you're going to buy a connector, they will say, oh, if you want to do this, buy this part, buy this part, buy this part. Yeah. There's all these material mismatches, all these kind of things that you could just get wrong. And why get them wrong when you're talking about a part that maybe instead of $1, it costs $10. It's not like any of these connectors cost hundreds of thousands of dollars. Let's be very clear.
Some
maybe
of them
not
cost
hundreds of thousands, but they're in the hundreds.
Yeah.
Some of them are quite
But that
expensive.
is what I'm getting at. That's very different than rocketry. Rocketry, actually, the connectors will get extremely expensive because they need to be much, much more vibration tolerant, be able to handle much higher loads and be sealed and all these different things that we don't have to do on spacecraft. I would actually say from an aerospace terms, spacecraft connectors are some of the weakest. And I mean, that's intentional. We don't need to carry the extra mass.
Right. But if you're comparing them to terrestrial common everyday connectors, they're way more robust than what you're using in, even in the automotive field. They're way more robust than that.
Absolutely. Absolutely. Okay. And then we have a question from Ethan. And it says, I'm not answering this one, Ethan. Thank you, everybody. We'll see you next episode.